Okay, so um, I'm sorry about the confusion about the take-home exam. I thought the exam of steepest descent and conjugate gradient were separate. So I thought last week should be steepest descent take-home and this week should be conjugate gradient. But in my previous lecture, in fact, I mentioned we're going to do take-home exam um, on the week of basically this week. So that was totally my fault. If you find any mistakes that I make, or if you have any questions, any request, you can let me know. Usually I'm quite flexible, but usually I will be fair. So I usually give you reasonable time or resource. Sorry. For example, there's one person asked me if the exam can be done in a different day because he has to go to a church or whatever on Saturday. But he made a mistake because he misunderstood my timing. My take-home exam starts at 9, finishes at midnight. So you have 15 hours to complete the exam. So I give you a long period of time. That doesn't mean the exam needs 15 hours. The exam probably only occupy your 2 or 3 hours to finish. So you can choose your time. If you are going to the church for 15 hours, then please make special arrangements. Okay. Otherwise, I think I give you enough time for exams. Okay. So, and if I make one exception for a person, that's unfair to others. So I try not to change my rules. However, you are still free to let me know about your conditions or issues. There's still possibilities for exceptions. For example, you're sick, right? But you won't be sick for every exam, right? You're not that weak, right? Anyway, that's what I want to say before I start. In today's lecture, we are on, let me see what day is today. 10th? Yes, April 10th. So today we're going to learn another unconstrained optimization method, which is called the conjugate gradient method. Okay, so from the name, you realize the method is using some kind of gradient information. So it's a method that tries to find the appropriate direction to perform its minimum search. So why there's a word conjugate in front of the gradient? Because there's a definition needs to be introduced at the beginning, and when I introduce it, you can hardly understand what it means. It's a little weird, but I'm going to give it to you anyway. So there's a definition. So we are going to define so-called the conjugate directions. Okay, so we are going to given a symmetric matrix, say Q, okay, and we are going to Q. Also, two vectors d1 and d2, okay. So these two are said to be so-called the Q orthogonal. Or there's a different name, conjugate with, I better use the other word, with respect to. Oh, by the way, if in the future you see WRT, that means with respect to. Sometimes when I was in USA, the professor give notes, they just WRT. They don't tell you what that is, but they will speak out with respect to, because we use it in many cases, so they don't like to write everything down. With respect to what? Q. If D1 dot Q dot D2 equals to 0. Okay, that's the complete, the entire definition. So what's going on? What's Q orthogonal? So we can recall the definition of two vectors being orthogonal to each other or perpendicular to each other. So let's just recall two perpendicular or orthogonal vectors. For example, u1 and u2. So u1 dot u2 equals to 0 when u1 is perpendicular to u2, right? This is what you already know. So what is this Q orthogonal? Q is like a transformation matrix, like a rotation or some kind of transformation. You can think of Q as a transformation to D2. Right? If you have a matrix multiplying a vector, you're transforming its shape. Right? Have you learned mechanism or kinematics? In kinematics, you have a lot of rotational matrix, right? Translational matrix, scaling. You usually have a matrix multiplying a vector. So the vector will change its shape. Or I should say change its form. Because sometimes it's a rotation, sometimes it's a movement, sometimes it's a scaling. So Q basically is a transformation. So it's like if you transform d2 by q, the resultant vector is going to be perpendicular to d1. So d1 and d2 are related in a certain way where we call it q orthogonal, which means one of the vector is being transformed into a new way. After transformation, d1 and d2 will be orthogonal. This is something like that. Okay? So the term conjugate means when you have two things, they are tightly connected to each other, and when you change one part of the pair, the other part will be changed simultaneously. Sometimes we use the word conjugate. So this name was utilized over here just to describe how D1 and D2 are tightly related. Okay, so why is this important in this method? If you, let me draw a picture. If you look at a very simple problem like this, let's say this is x1 and x2, and this function basically could be x1 squared plus x2 squared, the contour of it. And if you have a design point, and the negative gradient direction is this way. This is the negative gradient direction. Okay, and because this, in this circular space, this direction is pointing toward the minimum point. Okay, however, if you have a different space which looks like this, if you have a different space like this, this one could be, let me think, yeah, this one could be a function like this. In this way, if I find a design point somewhere here, the negative gradient direction would be somewhere over there, but not pointing to the center. So just like what we did last time in steepest descent, we will be moving zigzagging because we just don't know which direction goes to the minimum. Okay? So if I can kind of deform the design space in a different way and transform the space to space on the left, after transformation, probably I can move toward the center more easily. So the idea is a little like what I mentioned. If we can transform the space, it's possible that the new gradient direction in the transformed space gives us a faster direction that brings me to the minimum, takes me to the minimum. But that's just an idea. It's the way it's not. It's, I think, to think of this kind of definition in this way probably will help you understand why conjugate gradient behaves better than steepest descent. It's just I'm just trying to give you reasons why this is a good method, okay? But these descriptions doesn't help anything on the following derivations. The following derivation is long, and during the process, you sometimes it's hard for you to understand why are you doing this right at this point, because it's not straightforward. Okay. Anyway, I hope that helps a little bit. Now, okay, so let's recall the process of steepest descent. This time I can again use a drawing. So for example, here's the minimum, and let's say we start from here. So for example, that's my initial guess. Okay, so to move along the negative gradient direction, I probably will find the minimum right here, and then the gradient direction probably goes this way, so the minimum point probably is here, and then probably here and here, right? So let me make those nicer. I should draw in this way. Okay, so it's doing this kind of a zigzagging. And if I call this one as D1, and if I call this one as D2, they are basically the descent directions, right? They are the descent directions. And basically they are the moving directions for each iteration. So eventually you may have n of them. So let's say there are n vectors to find the optimal, for example, x star. Okay, so if that's the case, x star basically would be like a combination of vectors, like a linear combination. So you can even write in this way: alpha 1 d1 plus alpha 2 d2 plus da 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 plus alpha n dn. Okay. Of course, you need to add x, the initial guess, right? Starts from the initial guess, you move toward D1 by certain step size, then you move along D2 by certain step size. So alphas basically are the step size for each movement. For short, for the ease of later derivation, we can just assume this is at 0, because you can always claim your x star is a relative movement from yourself. You can treat yourself as 0. You can move the coordinate system to the on top of the initial point, and you can say, okay, over there's a point somewhere away from the initial point, and that's my x star. We can describe in this way. So the purpose of writing this formulation in this way is just to, so you can say this is the relative movement from the initial point, right? Because you're treating the initial point as 0. So what is the relative movement from the initial point, so that that final destination is my optimal? Okay, and as a result, from Stieglitz-Steenson, we realize I just need to move along n directions with n step sizes. At the end, I can reach to the optimum. Okay, now we are going to start to do something with it. We already introduced something called Q orthogonal. Let's try to apply Q orthogonal onto this equation. So we are multiplying using D1 and Q. We are using this to pre-multiply everything, everything in this equation. So what we will get at the end is something like this. So we will get alpha 1 d1 dot q dot d1 plus alpha n d1 dot q dot dn. We're just apply. This is a pre-multiply. Pre-multiply. Okay. So what happened is these becomes 0 if all the di and dj are Q orthogonal, right? As I mentioned earlier, if we have two vectors that follows Q orthogonal, d1 dot q dot d2 equals to 0. So that means d1 dot q dot d3, d1 dot q dot d4. Basically, if all these d's are Q orthogonal, then in this case, only the first term remains non-zero. The rest will be 0 if they are Q orthogonal, right? So, if that's the case, we can then rewrite this equation into the following form. We can determine Q1, not Q1, alpha 1, sorry. Alpha 1 basically is going to be this. So what does it mean? If you know D1, if you know where your X star is, and if you know Q, you just put them in this way, you will know what would be the step size for the first iteration. This information is completely useless. If I know where is the optimal, then I will just finish. But for the derivation purpose, this is one of the procedure. Okay? So at this point, this equation looks meaningless because I have no idea what is Q star. Now, we are going to recall another equation. Recall we're going to recall second order Taylor expansion. So second order Taylor's expansion. Okay, so let me write it down for you. It looks like this. X0 means the expansion point. I should write down this one in the second line because it's long. Okay, so just recall Taylor expansion. So if I rewrite this in a different way, it could be rewritten as the following form, and I will explain later. It could be rewritten as this way. We intentionally would like to rewrite in this way. In this case, basically Q is Hessian. In this case, Q is Hessian matrix. Right? So what is B and C? Basically, we will have a lot of coefficients for X. Like this is multiplying X, right? And you will have X multiplying Hessian and multiplying the X0. That's something multiplying X. So we will have a bunch of things multiplying X. Those coefficients in front will be combined together as B. If you spend some time to rewrite the second order Taylor expansion, you can derive what is B. Okay? And if you try to figure out what is C, basically, this is a constant, right? And x0 times gradient is a constant. x0 times Hessian times x0, this is constant as well. All these are basically a bunch of constant. We call the combination of them C. So C, we just use C to represent all the constant. Okay? So we just want to rewrite in this way. That helps us to do further derivation. So in previous knowledge, we know if we can find gradient equals to 0, that's where we can find the optimal. So in this way, this equation can actually be rewritten as Q. Actually, I should say at the optimal gradient equals to 0, right? So if we apply this equation to the equation above, at the end, we actually have something like this. This is after taking the derivative. And at the position of x star minus b equals to 0. This is after you take a derivative. So basically it's telling us q dot x star equals to b. Why do we do this? Because we want to replace something that we wrote earlier. Because right here there is a q dot x star. We have no idea what is x dot q star. But we can replace it, this guy. We can replace this guy by b. So we just found alpha 1 equals to d1 dot b d1 dot q dot d1. Okay? So that tells us how to determine the step size. If we know the step size, it's easier for us to know how far we should move along the D1 direction. And by using the same way, we can do it on D2 and then alpha 2, alpha 3. So I know along each direction how far I should go. But how do we get B? B basically is the, like I said, B is right here, right? B is the coefficient in front of x. So basically, it contains information of gradient, contains information of Hessian, and your expansion point. So that actually doesn't help much. Basically, I need to put Hessian and gradient information into B. Then I can know my step size. It's like Newton's method. I still use Hessian. But don't worry, this is just the beginning of the derivation. Okay, so up to now, you probably know nothing. That's okay. We are going to continue with the derivation. Okay, so just keep in mind, alpha could be deriving this way, but we are still not sure. Here's one thing. Still, at this point, we're still not sure if d, I, and dj are Q orthogonal. Nobody guarantee all the D's are Q orthogonal. So this is only true if all the D's are Q orthogonal. But at this point, we didn't prove all the D's are Q orthogonal. Okay, so at this point, it doesn't help. It doesn't help much. Okay, so we need to do something else. Now let's try to do something else. Let's now take a look at the second order Taylor expansion that I just derived. I just derived this guy. I need this for my following derivation. Okay, this is the second order Taylor expansion, right? So over here, I did this. I did this earlier at the minimum point. I told you the gradient of the function should be 0. This is what we already know in high school. Gradient equals to 0 give us the minimum point. We are going to use that idea again, but this time I'm not going to use this term Q to confuse you. I'm going to use gradient of f equals to 0 directly on the second order Taylor expansion. So at the end, if I take the gradient of f, in fact, what you will get is going to be like this, plus Bayesian dot. We derived this in the past. We did it in the past. So for derivation purpose, I need to make this description simpler. Otherwise, it will be too long. So I'm going to choose the kth. So basically, is the kth design point. As my expansion point. And I'm going to rewrite this as gradient f with a k as a subscript for short. This is just rewrite this like gradient fk for a shorter description or shorter form of this symbol. Similarly, I'm rewriting Bayesian as hk. Okay, so at the end, I will have gradient fk plus hk dot x minus xk. That's a simpler form. Okay, I'm going to call this equation 1 because later on I need it. I need this equation 1 later on. Okay. Next, from Stipe's descent. We would like to find our next point from the current point plus a step size and a moving direction, right? This is what we want to do in Stipe's descent. So over here, we can rewrite dk. What is dk? dk basically is No, 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 no. We don't rewrite decay. We ah we define. We will now define decay in a certain way. It's basically the let me make sure how to explain this. Okay, so if we are moving in this way, if we are moving toward the negative gradient direction, so I shouldn't say define. I should say where. Then this is the method of steepest descent. However, this time we are introducing a new method. So obviously we won't be moving toward the negative gradient directly. We obviously need to make a change. So we define our moving direction in this way, where I have a so-called beta k minus 1 and d k minus 1. So this is newly introduced. But why do we introduce in this way? So this is my current moving direction, and this is my previous one, previous moving direction. So I just define something like a step size. This is like similar to step size, or some kind of weighting coefficient. But unknown at this point. Right now, unknown. So we define a new way to move our design point. Besides moving toward, instead of moving toward the negative gradient, we want to make a change. So the change is based on the knowledge from the previous direction. However, when I introduce this previous direction, I need a weight in front of it. I don't know how much I need to utilize for this new term. I don't know what is beta, but it's basically a weight in front of my previous direction. I wish this will help me to find the minimum faster. So this is an equation that I define. I'm going to call this number 2, call this one number 3. Okay? So, now we have two unknowns. very important two unknowns. One is alpha k, one is beta k minus 1. These two are unknown. If I figure out what is alpha and what is beta k minus 1, and if these two are provided in an appropriate way, maybe this strategy will help me to find the minimum very efficient. So the goal of the following derivation is to find appropriate alpha and beta. So it's moving toward the minimum effectively. Okay. So one idea is that now we can say we design all the D's to be Q orthogonal. Not Q orthogonal. This time, Hessian orthogonal. So I shouldn't say all the D's. Sorry, let me rephrase. We design our moving directions in such fashion. We design dk and dk minus 1 as Hessian orthogonal, Hessian matrix orthogonal. Orthogonal. So we basically have a previous moving direction. When I choose the new moving direction, now let's say we are moving toward the new direction so that this new direction is Hessian orthogonal with the previous one. Why do we do that? It's like we are transforming the design space based on Hessian matrix, and when we transform the design space and if we move toward the orthogonal direction with respect to the previous one, we should be able to move toward the minimum very effectively. But you just right now you don't see it, but we just design this in this way and hope it makes sense, and we will prove it will make sense later on. So let's say this is by design, and since we design in this way, the following equation is valid. Okay? Since we design this way, this is valid. So I'm gonna call this equation number 4. Okay? So basically they are these two directions are now conjugate directions. Okay? So these are good for now, and we're going to restart some other part of the derivation again, and these equation 1 to 4 will be utilized later on. Okay. Like I said, the derivation of conjugate gradient is a little weird. It's jumping from here and there, and during the procedure you have no idea why we are doing this, but later on they will combine together. So this time we are doing something like this. Okay, we are checking our Taylor expansion again. So let me copy this to the bottom, so easier for me to do the following derivation. Okay, so basically I recall second order Taylor expansion. Erase. So I'll recall this, and yeah. So I recall second order Taylor expansion, and we already mentioned we apply the kth design point as the expansion point, right? So my kth point is my expansion point, and what you will get next is gonna be your x. So we're going to basically apply k plus 1 at your x. So based on xk, you should get xk plus 1. So basically your new point is xk plus 1. So let's rewrite the Taylor expansion in the following form. So we can rewrite like this. We can say this is k plus 1. This is k. And this is k plus 1 minus k, dot product radian k plus 1 half k plus 1 minus xk, dot product Hessian k xk plus 1 minus xk. Right? We can rewrite in this way. Okay, while you are writing this, let me check one thing. D and gradient 0. Okay, so next we are going to apply something. X here. We're going to apply equation 2. So let me copy equation 2. Copy equation 2, paste it here. So since we have this equation 2, we can then derive the above equation as alpha k dk gradient fk plus 1/2 alpha k square dk dot product Asian matrix dk. So what I did was, this guy is being replaced by this guy. So you will have this, this, and this right here. Right? I basically replace x k plus 1 minus sk by alpha k dk. And we know when we take derivative, we need everything to be 0 for optimal point, even when we have alpha. So what we want is we wish, at this point alpha is a unknown. So we wish partial derivative with respect to alpha k, we wish this equals to 0. Because if you have any variables, you at the minimum, even you take a derivative with alpha, it should be 0 as well. So this gives us, basically we take derivative with respect to alpha k. So at the end, you should have this guy plus alpha k times this guy equals to 0. Right? Okay? Now, we can rewrite the following. dk dot product, the following. Gradient, basically we just organize terms. We can put these together in this way. Basically, this and this is the same. I just take it outside of a bracket. And since dk cannot be 0, so what's inside the bracket must be 0. Right? Let me see. We need something right here. We need something. So that we can Ah, from here. Ah, from here. Yes. I told you it's not easy. So from here, from equation 1. Okay. So let me copy equation 1. Copy. Okay, and paste. And from, I'll just copy the whole thing here. Okay. Copy. Paste. So this is from since equation 1 was derived like this, and based on what we did earlier, we want to rewrite in the following form. This is the k plus 1, 1. This is the k1 dot xk plus 1 minus xk, right? And remember, from equation 2, we know xk plus 1 minus sk equals to alpha k dk. So we know this guy equals to this guy plus alpha k hk dot dk. Okay, and did you see this? This and this is exactly the same. Oh, h should be a matrix. They are the same. So from here I can plug in what you will get at the end. Dk dot gradient k plus 1 equals to 0. That's our equation 5. So it's a very not straightforward derivation. Okay? So how does it help us? That help us to do what? Let me see. We have this guy already. Yep. Okay. Then and we're going to call this guy equation 6. Okay? Yeah. Okay, I have those. Now, oh. Did we already do this? Okay, we have everything. Okay. Okay, so we can then, we have most equations that we need. We can do the following. We can recall 3. Okay, now it's like you are playing an RPG game. You need to get all the weapons. Then you can go out start to fight your enemy. So we have all the equations that we need. Now we are kind of putting things together. So from equation 3, this is from equation 3, we are going to this is a general equation 3, right? So if this is valid, the following equation will be valid as well if I add the index by 1. So the right hand side of the index will be adding 1 as well. Okay? Since we have this equation 3, so I'm gonna call this guy 3 prime. So it's like an additional expression of 3, but index plus 1. Now we are going to post multiply. H K D K to the equation 3 prime. We're going to do that, post multiply. So what we will get at the end is going to be dk plus 1 post multiply hk dk, and you will get negative gradient k plus 1 dot hk dk plus alpha k dk hk dk. Okay? And we know this guy is 0 because we design all of our d's as Hessian H orthogonal, right? We know it's 0. So at the end, you come up with an expression of alpha k, beta k. Because earlier we wanted to know what is beta k. Now we have one formulation for beta k. So if you know the gradient for k plus 1 design point, if you know the Hessian for Hessian matrix for the current design point, and also the moving direction of the current design point, this is beta. If we have beta, actually we can already solve for optimization, because beta tells us where we move. Initially, when we have steepest descent, we only move along negative gradient. But in conjugate gradient, we not only move toward negative gradient, we want to change the direction by a little bit. And how do we change it? We change by an addition of this previous direction. But what's the size of this addition? So the size of this addition is multiplying by this beta coefficient. Now we know what's beta. Beta is like this. So if we apply to that equation, we know in steepest descent, we not only move toward the negative gradient, we need to change the direction a little bit. So it's a beta multiplying your previous direction. However, it's not perfect yet because you still need Hessian matrix. If you still need Hessian matrix, basically it's Newton's method. You still need to occupy a lot of effort to compute Hessian. Newton's method. If you have Hessian, it's like a Newton's method. So the purpose of using steepest descent and conjugate gradient is to avoid using Hessian. However, when we derive, we still utilize a lot of information of Hessian because Hessian gives us the second order derivative knowledge, and that helps us to find the optimal more effective. Now we start from steepest descent. We are making cuts, linear cuts in the design space. We're moving zigzagging. Steepest descent move in this way, but not very effective. So we introduce conjugate gradient. When you move toward the negative gradient, you want to turn a little bit. From all the derivations we did, now we tell you, not only move toward the negative gradient, you should make a turn by adding a new direction, which is the previous direction. But how much do you add? Beta times the previous direction. But what is beta? Beta is here. Okay. So up to now, it seems like we have a new method, but not yet useful because we still need Hessian matrix for beta. So for the following, we're going to do more on top of beta, and we are trying to get rid of Hessian. If we can rewrite beta in a certain way so that we don't see Hessian anymore, then it's a success. Because you never need to do second order derivative anymore. Okay. So up to now, we are halfway done. Only halfway done. So let's see. Where are we now? We're up to here. Good. Okay. So in order to get rid of so we want to get rid of Hessian in this beta term. So I'm gonna call this guy and this guy separately. I'm gonna call this guy A. I'm gonna call this guy B. So I'm going to rearrange A and B so beta can be written in a better form. So now A, the term A equals to gradient f k plus 1 times Hessian k times dk, right? So let's take a look at dk from equation 2. Equation 2 is right here. Let's copy this guy. Copy and paste it here. So this was equation 2. We can actually rewrite dk in the following way. It's gonna be xk
xk plus 1 minus xk over alpha k. Okay, this is from equation 2. Now, we also want to rewrite from equation 1. So let's get equation 1. Okay, so copy the whole thing and paste it here. So this is equation 1. So from equation 1 we have this, right? So we can oh, okay. So over here you can tell there's a term right here, right? And that can be seen in equation 1. Exactly same thing. Not exactly, because we didn't put x plus 1 here. We should.
No, I just said A term, I think that should be the second line.
Yeah. I missed the k, yes. You're right. Okay, so from equation 1, the x is xk plus 1. So the red highlighted parts are the same. So we can rewrite this into the following form. We can rewrite in this way, right? And at this point, we're going to just rearrange the whole thing. And we're going to call this guy 7. Okay. And now we're going to deal with this guy. We're going to call this guy C. A lot of symbols. So let's handle equation, the term C. So C is gradient k plus 1 dot gradient k. Okay, now we are going to use equation 3. So let me get back to find equation 3. That's why we need all those numbers. Otherwise, you cannot find stuff. Oh, here, equation 3. Copy it. So over here, we're going to use equation 3. Sometimes I ask myself, how did the inventor of this method come up with all these equations? I couldn't know. I have no idea how they did it. They are mathematicians. They are just good in math. They're superior in math. We are just normal people. At least I can repeat what they have done and show you and make sense of it. Okay, now from 3 we can then rewrite this guy with what's in here. So we now have dot product, we will have this negative dk plus beta minus 1, k minus 1, dk minus 1. Yep. And we're going to expand everything. Plus beta k minus 1 gradient f dk minus 1. Okay, basically just expand everything. What's interesting about here is that from there was equation 5. Equation 5. Okay, let me copy equation 5. Copy it. From 5. We notice this guy is 0. The dot product between dk and gradient k plus 1 is 0. So we come up with something interesting. We can get rid of some terms. So at the end, I'm going to call this guy 8. Now, which one are we deriving? Okay, now we are going to play with 8. Okay, we're going to do something with 8. So, in order to further derive something on 8, we need to use 6. So let's get 6. Where is 6? 6 is here. Let's take 6. Copy it. Paste it here. Get rid of the line here. Okay. So now from 6 we can do what? Okay, from 6 we now know gradient f k plus 1 equals to this guy, right? So equation 8 becomes beta k minus 1 times gradient f k plus alpha k agm k dot dk dot dk minus 1. Okay? Before I do this, I want to reverse the order. So I'm going to reverse it. Reverse the order. Because when you have two vectors, a dot b is the same as b dot a. Because that's easier for you guys to understand when we see something right here. So if you reverse it, dk minus 1 is right here. Okay? So if we do that, 8 becomes this guy. Now we can expand the whole thing. Beta k minus 1, dk minus 1 dot gradient fk plus alpha k beta k minus 1 dk minus 1 dot Hasium k dk. Okay.
Now, this guy is 0 because the each orthogonal, and this guy is 0 because of same reason here. Same reason. Right? If dk dot gradient fk plus 1 equals to 0, you just minus the index by 1, that must be valid as well. So dk minus 1 dot gradient fk must be 0 as well. So at the end, 8 is 0. We just get rid of something. That's perfect. So what becomes 0? 8 was 0, so c was 0, c was 0, where's c? So at the end, this whole thing becomes 0. This whole thing, this is actually 0. So in equation 7, it's telling you that capital A term equals to 7. What is capital A? Capital A was here. So it's telling you in beta, the upper half, the term A, is 7. 7 is this guy. There's no Hessian in here. The magical part of this derivation is that originally the upper part has a Hessian inside. After all this long derivation, at the end, this A becomes something like this. No more Hessian. Just two vectors dot product with each other. Don't you think it's magical? I feel like I was amazed by the derivation. I can never figure out how they did it. I don't even know if it's one person or several mathematicians or whatever. Anyway, I feel magical. I feel like I went to a magic show. Now, the upper half, now we just put it back and see how how the beta looks like. Okay? So let's oh, by the way, my beta is my equation 9, sorry. Beta is my equation 9. So now let's put everything together, and let's just take what's necessary for the combination. So we had this guy, right? And we now have C. C is 8. 8 is 0. So we don't need C. We have A. We have this guy. Copy it. Paste it here. And we can get rid of all these, delete, and then move it to here, and get rid of this guy. Right? So from what we had earlier, we now want to combine these two. So combine these two. At the end, we have beta k equals to alpha k, and the upper half becomes this. But the lower half is not done yet. The lower half is not done yet. So now we are going to play with the entire lower half.
I'm gonna call this B prime. Okay? So let's play with this B prime. We're almost done. At the end, you don't need to memorize the derivation. You just need to believe it and then know how to use it. So today's lecture is just like a magic show for you. So the B prime, let's talk about the B prime. Alpha k, dk, hk, dk, right? What do we do with it? We multiply dk to it. Then we will have dk no, sorry. Not to this equation directly. We pre-multiply dk to 6. We need 6. So let's take 6 here, copy it. We need 6 and get rid of some terms. Okay, we need 6. Okay? So what we will get at the end will be dk dot gradient k plus 1 equals to dk dot gradient fk plus alpha k dk dot Hessian dot dk. Why do we do that? Because this guy is exactly this guy, right? So at the end, B prime becomes dk gradient f k plus 1 minus dk gradient fk. Okay? That's your B prime. And we're going to recall one of our good friends, which is number 5. 5 and 6. Actually, everyone helps a lot to get rid of some of those terms. So since we have this guy, 5, so this is actually 0, right? Then we can get an even simpler beta k. Gradient f k plus 1 dot gradient f k plus 1. Here we will have negative dk dot gradient fk. Yeah. Now we at the bottom part of beta k, there's no more Hessian. No more Hessian. Okay. In order to make it more useful, we want to rewrite the bottom part even further to a different form. In order to have
different format, I will need equation 3, I think. Let me find equation 3. Equation 3. Yes. Let's take equation 3. Well, 90% done. Paste it here. So from equation 3, we have this. We can then take care of B prime in the following way. Actually, B prime becomes negative gradient k plus beta k minus 1 d k minus 1 dot product gradient f k. Right? This is actually our B prime. So let's expand the whole thing. What you will get at the end is like this, minus beta k minus 1, dk minus 1. Okay. So did you see a good friend here? This is 0 for the same reason. If equation 5 tells us dk dot gradient k plus 1 equals to 0, you minus index by 1, dk minus 1 dot gradient fk must be 0 as well, because it's a general equation for all k. So b prime actually becomes this. So I actually should move this guy below and directly use this guy. Remove this, delete, use this guy, copy. Right. This is a more like a cleaner derivation. So this is our beta. No more Haitian. Just some gradients, dot product with each other, and then divided by each other, and then you got beta. Whew. Finally. Now, put it back to the beginning. Where's the beginning? Here. Okay. Now we copy the whole thing. This is what we had at the very beginning. Just copy it. Try again. Copy. After all these long derivation, now so this is from the beginning. I think I can just get rid of this guy. Delete. Remove. Okay, so this is what we had at the beginning. So now we can come up with the general equation for steepest descent. So general equation for not steepest descent, sorry, conjugate gradient. Conjugate gradient method. So in general, you are going to move your xk with
step size times moving direction, where how you compute decay? There are two ways. One is negative gradient when k equals to 0. Because when you start with k equals to 0, and there is no k equals to minus 1. So at the beginning, in the first step, conjugate gradient is the same as steepest descent. So first iteration is the same as steepest descent. Okay? How about the second iteration? The second iteration, you have, starting from the second iteration, you will have this so what is beta minus 1? So basically what you got above, you just have your index minus 1. That's it. This is the general equation. So what to do for truly use it? In the first iteration, just use it like steepest descent. In the next, starting from the second iteration, when you are applying this linear search, where is your moving direction? You will evaluate the gradient at the current position, plus there's a weight right here. The weight is going to be calculated by this current gradient dot product with itself divided by the gradient from the previous one dot product with itself. With this weight multiplying the previous moving direction. This will help you to find a better moving direction. How come? Because if you believe the current moving direction is Bayesian orthogonal to the previous one, and from the story that I told you at the beginning, if you have a design space like this, after Bayesian transformation, you will have a space like this. So if you move toward the gradient direction in this transform space, it should help you to reach the minimum more effectively. Okay? But once you know the general equation, all you need to do next is to use it. You don't even need to care about how it was derived actually, if you are not planning to improve the algorithm. So let me show you the solution process. So at the beginning, you will have your initial gas, and k starts from 0. So for every iteration, you will calculate the gradient at k. You will calculate that. Okay? With that, you can perform k plus 1 equals to k plus alpha k dk, where dk equals to negative gradient f if k equals to 0. Otherwise, dk equals to this guy plus current one, dot product current one, previous one, dot product previous one, now then multiplying the previous direction. Okay? But over here, you don't have your alpha, right? So you will need to do a line search as well. So I need some space from the right. Over here, you need to, actually I can copy what I showed you earlier in here. Exact same thing. Oops. Copy the entire, sorry, only I have copy, you don't. Shrink it a little bit. I don't have enough space. Man. No space. Then I need somewhere like here. Okay, I just need to do these. So over here, once you have that, you are moving on to a sub problem. So basically you are solving for an alpha minimization. Okay? And over here we only learn 1D Newton, that's fine. So once you're done, you basically update alpha k. Alpha. Update alpha k. Yep. That's how you do the sub problem. Then you will check convergency. So in our case, I usually will do k plus 1, k plus 1 minus xk, whether it's smaller than or equals to, for example, a small number. That's my convergence check. So if not converged, I need to move back to here with k equals to k plus 1. If not converged, if yes, then my optimal is my latest one. Okay. You may need to copy it from my PDF later on because it's a lot to copy. Anyway, this is the method that you can use line search and also effectively find the efficient moving direction without the needs of Hessian matrix. Now, I'm going to program this in MATLAB quickly, then you are free to go. Okay?
So if you cannot copy the whole thing, sorry, maybe you will do it after I give you the PDF. Now let me turn off this. Now, since I already have this steepest descent code, I can do something with it in order to generate a conjugate gradient code. So I'm going to save this as a new file. So I'm going to just do something with it in order to get conjugate gradient. So what you need to do is to memorize the previous moving direction and also memorize the previous gradient. So earlier when I have a gradient calculation right here, I need to memorize it. So whenever I get it, I will save it as a previous grad. So this is for the purpose of conjugate gradient. Okay, I just keep a memory of it. And also, this time my recursive formulation would be different. I want to define so-called the DIR, like a moving direction. It should be negative gradient, right? So, but this is only negative gradient if I'm in the first iteration. So I will say if my iter equals to 1, then my moving direction is going to be negative gradient. Else, my direction will be something else. So I will complete this line later on. For the general equation at this point, it's gonna be plus alpha times the moving direction. Okay, so all I need to do right now is to complete the second part of my if else. So supposedly this is gonna be current gradient dot product current gradient. So I basically need to transpose first vector times the second vector, that's basically dot product, divided by the previous ones. Previous. To avoid in unexpected calculation, I'm going to put brackets. So just to make sure they are being calculated in the way they are supposed to be. And then multiplying previous direction. So I need to memorize the previous direction. So if in every time I have a direction, I will have a memory of previous direction equals to dir. So here, previous direction. I think I'm done. If there's no bug, that's it. Okay, let's run it. Okay, something's wrong. Maybe I didn't use iter. What did I use? I use small k. So it's not iter, it's a small k. Okay, run it again. Okay, typo, transpose. Oh, hold on. There's no function called transpose. Sorry. In MATLAB, it's a Prun is transpose. Sorry. It's not Google Sheet. Prun is transpose. So a vector, and if you have a prun, that's transpose. So let's run it again. Something's wrong. Line 32. So let's see what happened. Let's run in the debug mode. Okay, so now I have gradient is a symbolic. Gradient, previous gradient, previous direction. Okay, is it hard for you to calculate this? My gradient is you mean vertical? Horizontal. Yes. So I should transpose on the other way. Thank you. I should transpose in the other way. So everything is horizontal. Okay. Let's see. No? Okay. Let me think about it. Previous grade direction is
多一撇，应该有一个多一撇。
here. Previous? Here. Oh. You are really suitable for graduate program. Okay. Something must be wrong. It's running, but it's not running in a good way. Let me think. Let me figure out why. Previous direction. Direction. Previous direction. Previous gradient equals to gradient. Negative gradient plus gradient dot product gradient over previous one dot product previous times the previous. So x alpha when we put back okay, where?
Previous gradient 应该是被洗掉了。
Previous
你的
gradient.
previous gradient 在这里，然后你的 gradient 结束了之后就把它更新，所以这两个是一样的。
So I should memorize it afterward. So should be somewhere here, I think. Yes. Let's try it. Yeah. So let's turn off conjugate gradient and see what it looked like in steepest descent. In steepest descent. In order to turn it off, I can just comment the additional part. Then this is basically steepest descent. So let's remind ourselves how steepest descent look like for this problem. So earlier we were doing zigzagging, and it took us 16 iterations. Now, just keep this in mind. Maybe I copy this somewhere. Just copy these right here so we can compare later on. And now let's turn on conjugate gradient. Just this extra term that help us to change the direction. And you can see only 6 iterations. And you can tell from the third iteration, it's already really, really close. We set up the convergency criteria quite tight. But conjugate gradient can already find almost optimal. It's just moving slowly at near the optimal. Okay? If we use Newton's method, only 2 iterations, because this problem is a quadratic function. Earlier we defined this function as x1 squared plus 10 times x2 squared. Like I said, Bayesian has a major magic of moving along. Bayesian has a magic of transforming the ellipse space into a circular space. So inside the circular space, when you move along gradient direction, it goes to the minimum right away. That's why Bayesian is truly the magic why for ellipse space it's still moving so fast. Okay. Do I have a Newton's code? Newton's method. Let me see. I didn't have it. Maybe here. Is it I think I didn't. I don't remember. Maybe I don't have Newton's code. Anyway, so from here you can tell, iteration-wise, it requires fewer iterations. Let's see how many times we need to call the function. Okay, we never talk about the numbers of the function calls. It's also a very important factor to evaluate the performance of a method. So right here, whenever we compute f, we will count the function call as 1. Let's see how many times we call f. So like this one right here, if I substitute, that means I'm calculating once. So whenever I substitute some value into f, that count as 1. So I will have a so-called function call counter. Initially, I will set the function call as 0. So whenever I substitute, I will plus 1. My function call plus 1. Over here, even I was using finite difference. When I add x1 or x2 by a small number delta, I still need to plug into f. So that's another function call, right? Right here. There's inside the there's a f alpha. That's another substitute. No, it's not yet, because it's a symbolic substitute. It's does it count as a substitution? Let me think about it. Not yet, because for x alpha is symbolic, we not yet put true number into it. This is in the subproblem. This is where we truly guess a number of alpha, and this is where we plug in numbers into it. So over here,
that counts as 1, and plus and minus. Yeah, these three are the times that we truly put a number into the function f. Actually, those are everything, I believe. Yes, those are the only times we plug into function f. And whenever I display the results, I want to display the function calls. So I should right here. Let me call that fc, function call. Okay, save it and play. So from here you can tell for every iteration I need 9 times of function evaluation. I plug into f 9 times actually. How come it's 9 times? For gradient you have the middle. For gradient, you need to compute, if this is the x1, x2 space, you have your current point, and you increase a little bit. This is your current x, this is current x, plus a small delta along the first direction. You compute here the current x plus a delta along second direction, and then that tells you that gives you a direction of gradient. So along some gradient direction, for example, if the gradient direction is here, and what we did was we compute we use 1D Newton. So along this direction, in order to move along this direction, this is basically along your D direction. Along D, is it along D? Yes. Along this D direction, we were trying to calculate alpha. So we use 1D Newton. And when we use 1D Newton, we need to compute f prime and f double prime. So we need to do two iterations. And every iteration in alpha search, we will need to compute its own, if we are searching at some point here, we will move a little bit forward and backward when we are doing alpha search, finite difference. Okay, so if this is the nth position, this is the n minus 1 and n plus 1. No, I shouldn't say plus 1 and minus 1. I should say it's the nth position with increment of delta. So this is like we were having a increment of delta and a decrement of delta in the line search. So we can have evaluation of f prime and f double prime. So basically you compute function value 3 times for one iteration, and because we have 2 iterations, so that's 6 iterations, 6 function calls. So here we have 3, here we have 6, totally we have 9 function calls. We can actually control how many function calls we want. Can anyone tell me, are we able to reduce the function call even further based on what we know? Actually, we can reduce by 1. Can someone tell me how? If we start with initial guess alpha equals to 0, basically the function evaluation is going to be at the same point. So when we are outside, when we are in the main procedure, when we compute this function value, we actually compute for a second time in the alpha search. That's a waste. For example, if one function evaluation costs you $100, that's $900 already. So in real life, when you are doing optimization, let's say you try to find the optimal parameter of some mechanical part. How do you optimize? It's not a computer, it's a real part. So what does each function evaluation mean? It means you truly choose the parameter for that particular design and then evaluate its performance. For example, if you are finding the most effective wind turbine, for example, wind turbine, and let's say there are several parameters to tune, and let's say one parameter is the length of the turbine, the other parameter could be the width, the other one could be the thickness, something like that. For example, 3 variables. So you will need to have your initial guess, and in real life you build it. You have your initial guess of your length and initial guess of your width and also thickness, and you build it. So what's the function you are optimizing? For example, efficiency, energy transfer efficiency, something like that. So you truly perform experiment of that initial guess and receive a value. That's your F. That's only one evaluation of one design. So what to do next? You change your first variable by a small number. For example, the length was 100 centimeter long. So in your next design, you increase a little bit. It's 101 centimeter long. Just change slightly. You build a new one with 1 centimeter increment of the length, and you do experiment to evaluate its performance. So you get the energy transfer efficiency of this particular design. And then for the third design, you don't do increment on that anymore. You increase your width. So for example, width was 10 centimeter, now it's 11 centimeters. So that's how, with these trials near the original design, you can compute the gradient. So then you have this gradient direction, and you will perform so-called the alpha search. And in real life, you try to reduce the amount of your trials, because every trial costs you time and resource. Let's say building a wind turbine like that costs you $100. This is already one iteration, $900. So from there, if we are, let's say you need 6 iterations. So 6 multiplying 9, that's $5,400. That's your advisor or your boss's money. They will feel painful if you do it wrong. Their money will be wasted. If, for example, like this student helped me debug. So he helped me. So my code was incorrect, now it's correct. So if in real life you were doing something wrong in the iteration process, then you will hear
the sound of money. Cha-ching, cha-ching, cha-ching. Right? So if you can reduce the function call by 1, that's saving money actually in real life. So like I said, in this particular problem, if you initially in the alpha search, if you guess alpha equals to 0, so it's like you are starting from here, you have a increment of alpha and decrement of alpha and increment of alpha along this way, and this function evaluation right here was computed in the main procedure. So this point was calculated twice in my code, in fact. So if I jump in and I remember my alpha initial guess was 0. So now if I replace so-called the F alpha current by the F value from the main flow, instead of truly computing it once, I will just directly use it from outside. Let's see what happens. So only for the if when my iteration is the first one, I will directly use what I had from outside, which is F current. And only if when my alpha search advances to the next iteration, I will truly compute the this is my initial guess, and if I move on to a different point, I truly need function value right here. But in the initial guess, I already calculate F once at the beginning right here. So I'm going to reuse it because the function value at the same point is the same, right? So let me try this, and if I'm right, I should get exactly same iteration procedure, but the function call reduced by 1 for each iteration. So let me copy all these. So you can compare later on. Just copy them right here to here. Okay. Paste them here. So I'm gonna compare with the bottom. So let's run the code. So let's now compare. Let's see. Numerically, they are exactly the same, right? If there's something different, if there's very slight difference, you will definitely see some difference. But if they are exactly the same, the procedure will be exactly the same. Right now you compare, everything is the same. Only difference is, in the previous code, I use 9 times for function call. But over here I only use 8 times. So for example, this is company A, this is company B. Company A spent $5,400 for completing this optimization, but company B spent $4,500. That's budget save, if you know what you're doing. Okay, if you can have a lower cost, you should be able to do better. Either earn more money for your company or spend your money somewhere else. Right? So, is it interesting? Okay, about the take-home exam, I'm going to give you mathematical problems. For example, it's gonna be like, please use steepest descent to solve this minimization problem. The initial guess is this guy. The convergence criteria are given as such. solve it. And maybe I will say stop at maximum iteration number 4. You don't need to go further. Show the procedure. So if you do not derive by hand, you copy from someone or you use my code to get numbers, you can never write down the procedure. So when it's okay to get, you can find your own way to get what you need, but you still need to write down the entire procedure, right? So I would say my code, you can use my code to just to check. So you can solve it by hand and then compare with computer to see, okay, yeah, I did it right. So supposedly I expect everyone to get 100 points because there's computer codes helping you. But the computer codes doesn't give you the details, the procedures. So you still need to spend time to write down procedures. And I'm going to give everyone different numbers for the problems. So there's no way you can copy your friend. If you want to help your friend, it's like you need to write the same problem twice. And I will make the exam long enough so that you don't want to do it twice. Imagine doing this, writing down in papers. How would you like to do it twice, right? So you can sit with your friend, let's do it, let's learn from each other and compare. So to make sure everyone got 100, that's fine. I'm okay with it. So there will be problems like that. I will ask you to solve by Stevens-Dietzen and also conjugate gradient. Okay. I will not give you example problems because this is already example problems in my code. Like this particular problem, solving x1 squared plus 10 times x2 squared is an example problem. Okay, but the problem I give you won't be that simple. It will be having more terms. You can use hand calculation, computer calculator. I won't even know. So you need to write down everything on the sheet. On Saturday morning 9 a.m. the exam sheet will be delivered, will be released, and in the sheet you will know how your problems is different from others. Basically, I will give numbers. For example, if you are this person, this particular number is this. You are that person, that number is the other number. So everyone is solving the same problem, but number-wise, it's slightly different. Okay? So from 9 a.m., when you see it, you have 15 hours to solve the problem. You can use up all the 15 hours, I don't mind. But in my opinion, I think you only need 2 or 3 hours for the whole thing. So you can do it anywhere you want. You can do it with or without computers. You can do it with or without calculators. Because over here, there's nothing difficult to compute. Everything should be able to be computed by hand if you want. Of course, with calculator, easy, more easy. This exam probably will occupy multiple pages. Write down your name and student ID on each page. By the end of the day, before 11:59 p.m., you need to take photos of every page. And I will tell you how to upload to me. So when you upload, No one else can touch your file. Only you can give me the file. So maybe either I will ask you to email me the file, or I will ask you to upload to Google Drive. Either way. So if I use Google Drive, everyone's sharing folder will be separate, so you can only access to your own folder. If you forget to upload your images, or you fail to upload those images, I have to say sorry. I cannot give you any excuse, because I have no control of your condition. So I recommend you to finish earlier and spend some time to handle the digital files. Give yourself at least 30 minutes to handle those images. When you complete uploading the images to me, I only allow one submission. So if you suddenly say, I accidentally missed one page, or I made some modification, the second submission won't be accepted. Okay, I only accept one. So you can spend your time to check if everything is correct before you submit. Once I get it, then you complete your exam. How about the paperwork? I need you to keep it and do not touch it anymore. Do not just do further. Just keep the original copy. On Monday, find some time to stop by my office and drop it. There's a box in front of my room. Just drop it in the box. So what I will do is, I want to make sure you truly have the paperwork, and also it's exactly the same as the photo. I will check it. It's to be fair to everybody. Okay, because you could be, if I want to cheat, if I'm a student, if I want to cheat, I can make multiple copies and share some copy to others. Then you guys only have one piece of paper. So if you want to cheat, you need to do it. Everyone needs to spend effort. Everyone needs to write down something. And I'm sure the procedure is so tiring so that no one wants to do it twice. So if you are truly with someone, and someone is like, you guys are having discussions and solving the problems together, that's fine. I consider those as learning. Okay? You guys learn from each other. And there will be a bonus question. There will be a bonus question. I recommend you to try it. The bonus question will be extra points. It's out of 100 points. It's an additional point. So you don't need to do it, but if you do it, it should be helping you to understand more about what I mentioned right here, about function calls. Now I'm going to tell you how that bonus problem will look like. I will create a Google form. Inside the Google form, there is a connected Google Sheet. Inside the Google form, you need to choose who you are and then make guesses of design points. And then inside the Google Sheet, you will see some function values, but you cannot see how the equation look like. So basically, you don't know what is the function. You don't know what's the function. You don't know its mathematical form. You don't know the shape. All you can do is to make guess. This Google system will throw a number back. So the procedure is just like evaluating the function, like in real life. When you make a guess of your wind turbine design, the only way to test whether it's good or not is to truly do an experiment. So substituting some numbers to the Google form and getting a value back is a procedure of trial. testing the function. So, since it's a Google form, you can keep on testing, you can do a stupid search to find the solution. So at the end, I will see how many times you need in order to get solution. So you don't truly need to follow this. You can just randomly guess. But I will make the solution so difficult to find, so random guess doesn't help. You need to manually try to follow some optimization procedure. So when you make a next guess, for example, if this is your initial guess, when you make your next guess, you will know what to do. But this time it's not by hand or by computer, it's by plugging design points to a Google Sheet, and the sheet will tell you a value. Okay, so that's the bonus problem. You may be confused or curious about how exactly it look like. I will make an introduction video of the procedure so you will realize how to do it. But it's also within the 15 hours. I only allow you to do it within the 15 hours. So that's why it's for bonus. And the procedure can only be learned from my introductional video. So I don't want it to be inside the 100 points, because someone may not be able to access to Google Sheet or Google Form. Okay? So that's everything I want to say about conjugate gradient and also take-home exam. Any questions? If you have questions, please let me know. Send me messages, send me emails. I'm very happy to help you. Sometimes when I announce a message from internet, I say something in a very restricted sentence. For example, I said, no excuse. You can only do this, do that. It doesn't mean I'm a mean person. I said those rules just to be fair, okay? But that doesn't mean I cannot make a change. If I said something, I mentioned some rules, if I'm wrong, you can let me know. I can make a change, okay? Any questions for today? Is conjugate gradient confusing? Is this confusing? Is this confusing? Only difference is this part. Compared to steepest descent, only difference is right here you add one more term. Forget about the derivation. Just memorize this one more term. And it's quite simple. From my code, you realize there's only several more computer lines compared to steepest descent. Okay? I have been uploading my teaching videos on YouTube. If you miss anything, feel free to go up there and watch it once, twice. Watch it, listen to it when you try to go to bed. If you cannot fall asleep, that will definitely help. Right. Okay, that's it for today. If you still want to talk to me, I will be staying here for 10 minutes. Otherwise, you're free to go. Okay, bye-bye.